Should we start, sir?
I mean, check up how many people are there and whether you want to wait or whatever.
Only 3 people are there, sir.
What happened to all the people?
I think people mostly watch offline. Means after this, not live. Because I see viewership goes up by about 60 or something in a day.
What is that? Viewership goes up?
Your voice is not clear. Can you increase the volume?
Now, what did you say? Viewership goes up what time?
So by one day, it goes to about 60 something, 60 or 70.
All right.
We are live. Okay, so we are live. Let me start. Okay. Okay, good afternoon. So today will be the last talk of the first section of the high pressure physics course. So I will continue with the phase transitions under high pressure part 2. So in the last talk, I discussed about phase transitions in general. Now I will take over from here to phase transitions under high pressures. So in the last talk, I discussed about Landau theory without any external field. In this talk, I will talk about Landau theory and effect of the external field on Landau and the Landau free energy. And then I will give a brief introduction how Landau theory can be used for studying pressure-induced phase transitions. Subsequently, I will talk about symmetry systematic and the mechanics of pressure-induced phase transitions. So this is something that I discussed very briefly in the last talk when we classified the phase transitions under high pressure in terms of symmetry. And at the end, I will give a brief introduction to the plastic strain-induced phase transitions, which is a thematic area of high pressure research recently coming up. And I will discuss about this in detail in the next part of my talks in somewhere in April. There are 3 talks dedicated for plastic strain-induced phase transitions. So in this talk, I will just give a brief introduction to the plastic strain-induced phase transitions. Okay, let us come into the first point of the talk today. So I discussed about Landau theory of phase transitions under no external field, which we said that Landau basically formed a free energy. Give a free energy, which is described as the power factors of this order parameter. Different ordered terms of this order parameter, and this is used to describe the phase transitions. So this is the order parameter is something that has non-zero value below transition temperature, and it has 0 value above transition. So order value is something that describes the phase transitions. So what we discussed in the last talk, that if we consider continuous phase transitions, we need just 3 terms, the quadratic term and to the power 4 term. And here, if the B coefficient changes sign as the temperature crosses this Tc, so there will be a negative B below Tc, which corresponds to the minima of this Landau free energy at some order parameter value more than 0, like this as shown in this figure. So I am talking about the symmetric Landau free energy with respect to the order parameter. So this curve corresponds to the Landau free energy when the temperature is higher than Tc, and this Landau curve corresponds to the temperature equal to Tc, where you see a lot of order parameter values becomes accessible, so there are a lot of fluctuations. And as soon as temperature decreases below Tc, you start getting a minima in the free energy at some order parameter value not equal to 0. So this is clear-cut indication of the continuous phase transition or second order phase transition. And you can see in this plot of order parameter versus temperature that order parameter gradually increases from 0 to some finite value as it goes to 0. Now, Devonshire included one more term, which is the sixth power of this order parameter, in order to describe the discontinuous phase transitions. Or in unfirst criteria, it is a first order phase transition. So in this case, the order parameter has zero value up to certain temperature, and there is a discontinuous change in the value of order parameter at some temperature, and below which it increases with some systematics. So in this case, in order to show that this order parameter basically arises discontinuously, we can see in this plot here. So there are two characteristic temperature in this case, which are called spinodal temperatures. So one temperature corresponds to the inflection point for the daughter phase, and other temperature corresponds to the inflection point of the parent phase when the daughter phase becomes more stable phase. So you can clearly see in this plot, as the temperature decreases, you start getting one minima here, local minima. So it still the energy is higher up to this temperature. But at this temperature, when T equal to some T naught, T equal to some Tc, this basically has three stable equilibrium positions, right critical point. And then at subsequently lower pressures, lower temperatures, you start getting this non-zero order parameter discontinuously arise. Now let us see what happens when we introduce external field. So first, let us consider the energy response of this free energy with respect to the order parameter. So as the order parameter changes, how free energy changes? We can define this sigma as the response of the system as the order parameter changes. So we know from thermodynamics that if we introduce some field, which is a conjugate variable of this variable, so we have to take the Legendre's transform of the free energy. So in the same manner here also, because the sigma here is the Legendre transform, the conjugate variable of this order parameter. So in order to have free energy, in case of external fields, we have to modify this free energy. Now there will be another term which corresponds to the coupling of this external field and the order parameter. So now the minima of this free energy will describe the phase transitions. So let us consider this case where there is no field. So minima is anyway defined by this equal to 0, and we have already discussed it. We have this kind of free energy curves, evolution of free energy curves at the temperature. Now, when we apply this external field, now it depends where we are sitting, whether we are at temperatures greater than Tc or we are at the temperatures less than Tc. So if we are at the temperature greater than Tc, what we see, the curve has only single minima. And that minima is somewhat different from 0. So as you as you go on increasing the this external field, what will happen that this minima will go on shifting. So it does not correspond to any phase time. Whereas if we have this field below critical temperature, we see this kind of double dip curve, and this can signify a phase transition. So this will become more clear as we see the plots between the order parameter and temperature. So this is the first case that I told. So in this case, we are looking at free energy curves at different fields, external fields. So this curve shows the order parameter as a function of temperature. The dotted lines are basically the behavior of order parameter under no field. So in this case, you can clearly see the order parameter was 0 up to certain temperature and then increases. So this clearly shows the second order phase transition or continuous phase transition. Whereas as soon as you apply field, what you see, even at temperatures very high to Tc, there is some value of this order parameter. And as you go across Tc, you see a continuous change in the order parameter, but this is not characteristic of any phase transition. You don't see any jump in the order parameter, and now you see the order parameter changing from 0 to some value. So what essentially this means that there will be no phase transition if you have an external field and the temperature is higher than Tc. Now consider other cases. When you apply field below Tc. So this is depicted here. So this is the free energy in case there is an external field. And you can see when there is no external field, you have a symmetric Landau free energy curve, which is similar as I shown earlier. But as soon as you change this field, you start getting some dip. And these dips basically corresponds to discontinuous change in the order parameter value. This is more clear in this order parameter versus external field plot. So this curve corresponds to T greater than T. We discussed earlier. It does not show any phase transition. And this curve corresponds to the isotherm which corresponds to Tc. At Tc, how order parameter changes with the external field. So this shows a continuous phase transition. But as soon as you go below Tc, what you see, the order parameter changes discontinuous and it shows a hysteresis. So if you go from this direction, you can see the order parameter has some value like this. And if you go from this direction, the order parameter has some value like this. So you have two critical field values in order to have this phase transition. So this hysteresis is clearly a signature of first order phase transition. So of course, here is the case I am considering where the order parameter is symmetric about the free energy. It means minus E and plus E, both values are possible. Now let us consider, okay, before considering other case where the first order phase transitions, let us conclude whatever inference we get from this analysis. So one thing is that the temperature induced phase transition is of second order if the external field vanishes. So there is no hysteresis. This is the case when there is no field. And then there is no temperature induced phase transition if an external field is applied. This is the first thing that we discussed. And then there is a no field induced phase transition at T greater than T. And we can talk about field induced phase transitions only when T is less than Tc. And the nature of this phase transition is of first order and it is associated with the hysteresis. Now let us take the second case. When we are considering the first order phase transitions using the Dewan-Shah theory, here we have included one more term. So in case there is no field, we have this kind of free energy curves where the king appears at some value where the order parameter has non-zero value and this phase becomes stable phase. We have a discontinuous change in the value of order parameter. Now let us see what happens to this order parameter versus temperature plot when you have different stress values. So this curve basically shows the transition when there is no field. So up to certain temperature, you have initial phase and then suddenly your order parameter changes and follows this way. This is a signature of first order phase transition when there is a no field. Now what happens when we apply field, but still the field is less than some critical value? In this case, you get this kind of curve, which has some instability region, which is represented by this dotted line. This is similar to PV isotherm in case of liquid gas transition, where we have some instability points and we have some spinoidal regions or metastable regions. In this case, again, it will be first order, but the hysteresis will be smaller. And as you go on increasing the stress value, you can reach a point where the phase transitions become second order. There is a continuous transition. So you reach a critical point. So in first order phase transitions, you can have a critical point at some external parameter value. So this becomes more clear in this plot where I have plotted the external field versus order parameter. So as I discussed earlier, this external field is nothing but the conjugate variable of order parameter. So it is the derivative of free energy with respect to order parameter. So if we take a parabolic shape or nearly parabolic shape of order parameter, the derivative will be something like this. So this is the case when there is a no phase transition. Now at t is equal to Tc, which corresponds to the second order of phase transitions, what you see this kind of curvature here. So this basically describes the instability of this external field, instability of system with respect to the external field. So this is the signature of second order phase transition. Now below Tc, the curves behave like this. So your external field reaches some instability point, and then suddenly system transforms to some other configuration corresponding to this field versus order parameter relationship. So this is a signature of first order phase transition. As you reduce this external field, the system goes back to initial phase, but with some hysteresis. So this is reversible phase transition, but with some hysteresis. Now, if your temperature is further lower than some sphenoidal temperature, in this case, even if you completely remove the external field, your phase will not transform back to initial phase. So you have to apply field in opposite direction in order to reach the field. So this is, if you have suppose one directional order parameter, means it is not symmetric, free energy is not symmetric. In that case, this will correspond to the irreversible phase transition. And if your temperature is further lower, then there is very little scope for this initial phase to exist. So only stable phases are your two transformed phase corresponding to the two different non-zero order parameter values. Actually, these are the curves that describes the behavior of martensitic phase transitions. In case of martensitic phase transitions, we describe the phase transition in terms of strain as an order parameter. So this sigma, this basically the external field is actually stress. So it is nothing but stress strain curve describing the martensitic phase transitions, which takes place by some coordinated movement of atoms, very small displacement. Actually, this is the case which is very relevant for high pressure phase transition, as we will discuss shortly. So indeed, there is an effect of external field on the behavior of phase transitions, as we have seen in both case of continuous phase transition and discontinuous phase transition. So from this also we can conclude some points that phase transition, first order temperature induced phase transition with hysteresis below some critical value of external field, and then first order field induced phase transition between low and high temperature phase in the range between the critical temperature and some T2 temperature, which is one of the sphenoidal temperatures, and then first order field induced phase transition between different orientation of the low temperature phase in the range less than T1. So here the initial phase does not come, though both the transformed phase of different order parameter are stable phase. And another interesting point in this case, there is an existence of critical point. So these are the conclusions we can draw for discontinuous phase transition under external field. So as we discussed, we can, if we describe phase transition in terms of strain, for example, in case of martensitic phase transition, this external field is actually stress. So we can describe pressure-induced phase transitions with this way, considering strain as an order parameter. So I will just briefly discuss how Landau theory is extended to describe pressure-induced phase transition. So in case of pressure-induced phase transition, if you see volume versus pressure plot, so initial phase, actually the volume decreases, and this decrease is nonlinear as we discussed in the equation of state torque, because as you go to higher and higher pressures, the compressibility reduces. So your bulk modulus increases, and that's why there is lower change in volume as you go to higher pressure. At some pressure, there is a phase transition. For example, let us consider first order phase transition. In case of the first order phase transition, we have some transformational strain. So there is some strain which corresponds to this transformation of the phase to this phase. And then again, the second phase follows some equation of state. So in case of high pressures, if you consider total strain, so total strain will have two parts. One is the elastic strain part of the initial phase, and then we have the transformational strain, which is a spontaneous strain, plus some strain corresponding to the second equation of strain, second phase basically. So if you want to formulate a Landau theory for pressure-induced phase transitions, we have to deal actually with large strain or finite strain basically. So the Landau theory has to be developed in basically terms of finite strain in order to describe pressure-induced phase transitions. And significant work has been done by this group, and I recommend you to go through these papers in order to see more detail how they have described pressure-induced phase transitions in terms of finite strain Landau theory. So basically, as we discussed earlier, in the Landau free energy, in case of external field, we have a Landau free energy, which is based on the order parameter, basically higher order terms of the order parameter. And then we have some correction to the free energy corresponding to the coupling between the order parameter and the external field. In this case, in high pressure case, we have to add one more part, which corresponds to basically elastic free energy corresponding to the first phase. So because our first phase itself is transforming, means basically it is not transforming to another phase, but it is evolving, and there is some elastic strain continuously building up. So this actually acts as a background for this phase transition. So this part also has to be included in the Landau free energy. And this way, the high pressure phase transitions can be described with the Landau. Of course, this theory can be applied to the cases where still the spontaneous strains are small, and there is some group-subgroup relationship between the initial and daughter phase. Because Landau theory, actually, here you have to describe the free energy, which describes both initial and daughter phase. So there should be some group-subgroup relationship. Of course, there are efforts where people are now trying to describe reconstructive high-pressure phase transitions, where we don't have any group-subgroup relationship. But if you have some pathways, and you know how these atoms are moving in order to go from one phase to other phase, you can still try to describe the phase transitions in terms of Landau. But as I told earlier, the Landau theory is basically phenomenological theory. So it can talk about the general aspects, macroscopic aspects basically. And for more detailed understanding, it is better to have the atomistic mechanism approach, and can have the inputs from theory in order to understand the phase transition compatibility. And that becomes more important even in case of reconstructive high pressure phase transitions. Okay. Now let me come to the symmetry systematics and the mechanisms of pressure-induced phase transitions. So as I discussed in the earlier talk, the high pressures basically suppresses diffusion, because the potential, interatomic potentials actually steepen when you apply high pressures. And so phase transitions basically takes place by a very small movement of the atoms. And many times there is a symmetry relationship between initial and daughter phase. So what kind of distortions, what kind of displacement we can describe? So just like martensitic phase transitions, there can be two kind of this coordinated motion, or basically this movement of atoms. One is the lattice distortive strain, which basically corresponds to the dilatation or distortion of the entire unit cell. This can be a homogeneous strain, and then there is a possibility that there can be shuffle. So if you have a unit cell with more than one basis, and there is movement basically some relative movement between these bases and it freezes to some position, then this corresponds to the shuffle kind of strain. So your phase transitions can be either purely corresponding to the homogeneous state or can be purely corresponding to the shuffle or maybe combination of these two. So if suppose we have a shuffle, we can describe the shuffle as some periodic function because you have a long range ordering in crystals. So the shuffle also should have some periodicity. So we can describe this displacement in case of shuffle as some periodic function where Q is the momentum vector basically, and that is related to the ordering, long range ordering of the system. And this shuffle displacement would be brought about softening of specific vibrational mode. So whenever there is a shuffle, basically there should be some vibrational mode that correspond to the oscillation of these basis points relative to each other. So some vibrational modes correspond to the motion of this basis point. Now when this shuffle kind of strain happens and system goes to the transform phase, they actually freeze to the new positions. So the corresponding mode, vibrational mode, should basically soften. This is the signature of the phase transition. Such phase transitions have symmetry relationship as I discussed earlier. So if there is symmetry relationship, we can in some manner use the Landau theory to analyze this phase transition. So now I will come to the systematic classification that is given by Dr. Gupta and Chidambaram in this paper. So we can broadly classify this high pressure phase transition in 4 groups. One is the isosymmetric phase transition where your initial phase and final phase have same symmetry, and in many cases it is isostructure. It's entirely same structure but different volume. There is a volume chart. And then there can be group subgroup relationship. So the daughter phase is a subgroup of the symmetry of the initial phase group. And then there can be some intersection group relationship. Means there can be some intermediate phase which is symmetrically related to the parent and the daughter phase. And then there can be one case which is called order disorder phase transition, in which the symmetry is lost. There is a drastic change in the long range order. So examples is the pressure-induced amorphization. Other than these, actually this list covers many of the phase transitions at the high pressure, but other than these, there can be reconstructive phase transitions also, which does not have any symmetry relationship. For example, graphite diamond transition. So those kind of transitions can be better studied by studying the atomistic evolution of the system by some theoretical calculations. Okay, now let us discuss the Landau free energy corresponding to these strengths that I discussed earlier. So this this analysis was given by Sir Lingard in this paper, and he basically expressed this Landau free energy as the power series of both kind of strengths. So your epsilon 1 is the homogeneous strain and your epsilon 2 is the shuffle strain. So you have higher order terms from both homogeneous strain and shuffle strain. And then there is a term which corresponds to the coupling between these two strains. So based on this expression, we can try to understand different classes of the phase transitions based on the symmetry. So now, if you consider the equilibrium of the system, so in case of equilibrium between these strains, we get this kind of expression between the homogeneous strain and the shuffle strain. So if we substitute this in the expression, we get this kind of free. And as I discussed earlier, there can be cases where there is only homogeneous strain, or there can be cases where there is only shuffle strain. In that case, the free energy would look like this. Now we will discuss in these 3 cases how we can address the phase transitions and how to study them, how to get the idea of mechanism of phase transition. So if you have either pure Okay, one thing I did not tell, this C, the C constant, this C constant actually corresponds to the modulus of this homogeneous stream. So somewhat related to the elastic constants of it. And this omega, this actually corresponds to the shuffle strength. So this basically corresponds to the frequency of the phonon mode, describing this shuffle. So in case of pure homogeneous strain related phase transitions, this expression describes the phase transition. So as we discussed in case of Devonshire theory, this B, actually this has to turn negative in order to make it a first order phase transition. But if we have a B positive, then how will this phase transition happen? So in this case, this C actually starts going down, so it softens. So elastic constants soften. And it is the softening of elastic constants that leads to this phase transition. So basically phase transitions would be of second order, continuous phase transition. Whereas in this case, when you have only shuffle strain, in this case, again, when B2 is negative, is the first order phase transition. But when B2 is positive, then this has to suffer. So your phonon mode corresponding to shuffles needs to be softened. So then we get the second order phase transition. Whereas in case when you have both homogeneous strain and this shuffle strain, in that case you have this kind of free. So here, if this expression is positive, considering that there is no evolution of this expression, this term with respect to the pressure, then this again the phonon mode corresponding to shuffle has to soften in order to give rise to this phase transition. But as you increase pressures, this elastic constant, basically this modulus, this can also soften. And as soon as it softens, it can lead to negativity of this. This term can become negative. In that case, even before the phonon mode softens, there is a possibility of getting this phase transition. And this will be mainly first order kind of phase transition. So now let us come to the different classes of phase transitions. So isosymmetric phase transitions, in this case, as we discussed, is basically same symmetry of initial and outer phase. And this kind of phase transitions generally don't involve this kind of strains. And there is a volume jump. There is a volume jump in initial and outer phase without change in symmetry. So you can talk about the volumetric strain in this case. So for example, this cesium. So mainly the driving force for this phase transitions are electronic instability. Like in case of cesium, as you increase pressure, the S band, the increased energy of S band actually increases. And so there are electron transfer to the D band. And this D band basically localizes these electrons. And this gives rise to a volume collapse in the structure. So like in this case, you can see there is a volume collapse from FCC to FCC about 9%. So this is a kind of phase transition, this isostructure, isosymmetric phase transition. Similarly, in case of cerium, you see there is a 17% volume drop at pressures at 0.7 GPM. And here again, there is an electronic instability that gives rise to the phase. So there are many explanations. First one was based on the 4F electron. So 4F electrons basically delocalize. This was the theory, earliest theory given to describe this phase transition. But there are many more theories based on Kondo effect, Yan-Teller, mixed valence, which try to describe this phase transitions. Even still there are papers coming which try to describe this phase, not clearly understood. Okay. Now let us take an example of the subgroup kind of phase transition. So I take a classic example of the FCC to BCT transition in Fourier. So any FCC structure, in any FCC structure, you can make a tetragonal unit cell by joining these phase center atoms like this. So as far as the system is in FCC phase, if you compare the C by A ratio of this data, it will be 1.41, basically square root of 2. So as soon as the value is square root of 2, it is in the FCC phase. But it has been observed, like in this case of thorium, at about 80 GPa, and the volume drop at about 0.6, when V by V naught becomes 0.6, you start getting increase in this C by A value. So this is clear-cut signature of phase transition. Here, this tetragonal sweet cell, it has a symmetry which is a subgroup of this FCC. So this is an example of group-subgroup transition. Now, because it is related from group-subgroup, so it should be described in the framework of the, it should be describable in the framework of the Landau theory. And their publication has been actually shown that how this potential wealth changes. If you plot this free energy as a function of the C by A ratio, actually you can make it C by A minus square root 2. So this will become 0. So this corresponds to initial phase, this dotted line, where the minima is at the C by A ratio of 1.414. But as you increase pressure, this energy well actually modifies, and you get this 2 minimum lengths. So this clearly shows this is a phase transition, kind of continuous phase transition, because this C by A ratio continuously evolves from this value. Now let us come to another example, which is example of the intersection group. This is the omega beta, famous omega beta transition in the zipper. This happens under pressures at about 35 GPa. So this is understood in terms of the collapse of these two planes. So if you take a BCC phase along the body diagonal, so you have atoms sitting like this. So as soon as it goes to omega phase, you can consider these two planes collapsing on the same plane. Now this atom basically lies on this plane, which is at one point, mid of these two planes. So there is clear-cut pathway for the omega to beta phase transition, and for that one has to consider basically there is no group-subgroup relationship directly. So we have to consider another space group, which is related to both initial and final space group. So it has been shown that basically this intermediate structure as a space group of P3 by R. And this is the subgroup of both alpha and omega. So it is the beta and omega phase. Okay. So as we discussed earlier, in case of this kind of phase transition, where the softening is happening because of some symmetry change, and then it should be related to some phonon mode, because it is a shuffle kind of thing. So there should be some phonon mode which should be softening, which describes this phase transition. And indeed, from calculations, it has been shown there is a longitudinal 2/3 BCC phonon mode, which actually soften across this phase transition. So let us take another famous example of intersection group transition. We know silicon actually transforms to many phases. It has a rich phase diagram under pressure. So initial phase of silicon is a diamond phase, and at about 12 GPa somewhere it goes to the beta-tin phase, which is a tetragonal phase. And as you further increase pressure, it actually transforms to the primitive hexagonal phase. But again, this transition is also through some intermediate structure. The intermediate structure which describes basically symmetry of both these structures. So atomistically, you can consider like this. So this is the unit cell of your beta-tin phase, and this unit cell, these atoms, if you take these atoms and you introduce some movement, shuffle movement to these atoms like this solid atoms, solid circle atoms, black atoms. If you move these atoms like this, you can get the primitive hexagonal phase. So in this case, again, there should be a phase, intermediate phase, which would be the subgroup of the group describing the symmetry of the initial and daughter phase. And there should be some phonon mod which will soften to describe this phase term. And indeed, it has been shown in this paper by Dr. Sharma and Sikka that if you consider an intermediate orthorhombic cell, then in this case, the zone boundary mod is half 101 pH mod. This actually freezes. And this corresponds to the displacement of about C0.8, and this gives rise to this phase transition. So there is an intermediate phase in this case also. So generally, this intermediate phase may not be evident when the phase transition happens if the phase transition is very rapid. But if it involves some barrier, so in that case, it is a possibility that this intermediate phase can even be seen in the experiments. In fact, now if you see the phase diagram of silicon, people show some intermediate phase between the beta tin and pH phase, and that is the iron phase. So this is the intermediate phase between these two phases. This is another classic example of sodium, in which at low temperatures, at high pressures, it transforms to BCC to HCP. Now, in this BCC to HCP phase transition, we can understand it like this. So this is your BCC unit cell. We take the 4 unit cells, and this is the HCP unit cell that becomes the structure after the phase transition. So what you need to do is this sum of the atoms has to move in this direction, and then this angle. So basically the axis has to suppress such that this angle becomes 120. So when it becomes 120 degree and these atoms move by some amount, then you get this phase transition from the BCC to HCP. Now again in this case, the intermediate phase should be an orthorhombic phase. And from calculations, it has been shown that the intermediate orthorhombic phase, which basically changes structure from BCC to HCP phase, the energy differences are very, very small. There can be many orthorhombic configurations between this path, and the energy difference are very small. So when you do in experiments, there is a possibility that you can have the ensemble of this orthorhombic phases. And that is the reason when you do XRD measurements, you get very broadening, the peaks actually gets quite broad when the phase transitions takes place. So this broadening can be explained by the ensemble of the intermediate orthorhombic CMCM. So this way we can understand the mechanism of phase transitions and also try to describe these phase transitions with the Landau theory. Of course, one more case is there, the order disorder phase transition. In this case, the daughter phase is an amorphous phase. So energetically, if you see, amorphous phase should not be a stable phase. So in a sense, it should not be a thermodynamic phase transition. But still, we observe in many cases this order disorder phase transitions. Like in lithium potassium sulfate, in silica, in AlPO4, and many of the negative thermal expansion materials like this zirconium tungsten. So in these cases, when you apply pressure, you get amorphization. And there is one case of AlPO4 where if you take the single crystal of AlPO4 and if you apply pressure, it goes to amorphous phase. But on release, actually it comes back to the crystalline phase with original orientation. So it shows some kind of memory effect on. So the atomic displacements corresponding to this order disorder phase transition are somewhat displaced by, which leads to this. And there is one more inference that we can draw from this thing, that this cannot be this disorder phase or amorphous phase under pressure, like amorphization under pressure. This should not be thought of similar to melt quench phase. Because if the phase is melt quench, like the glass phase, you have an isotropic physical property. Whereas it has been seen that if you take the amorphous phase, which is amorphized after pressure cycling, you get an isotropic elastic property, which is clearly indicated that this pressure-induced amorphous phase should not be considered equivalent to the melt quench phase. So, in order to get more detail about this disorder transition, one may go through this nice review article by Dr. Sharma and Sipra. Okay. So now with this, I discussed more or less the symmetry aspects of the high pressure phase transitions. Of course, there are many more phase transitions under high pressures which are of interest these days. So I talk mostly structural phase transitions, whereas there can be phase transitions related to some emergent phenomena at low temperatures, where this correlation effects becomes dominant and they start playing role. Like there can be superconductivity transition, superconducting phase under pressure at low temperatures. And there can be some exotic phases, non-stoichiometric phases that can come at high pressure, high multi-megabar pressure. So these kind of phase transitions will be discussed later by my colleague, Dr. A.K. Mishra. So with this, I mostly complete this structural aspect of the phase transition at high pressure. And now I will give little introduction to the plasticity in the phase transition, which I will discuss in detail in subsequent 3 talks once the experimental and theoretical part is over. So, what is the difference between pressure-induced and plastic strain? So, as we discussed just recently, that this high-pressure phase transitions basically happen with very small movement of the atoms. Mostly, they are displacing time. Now, it is very much similar to the martensitic kind of phase transitions. And we know that martensitic phase transitions actually start at some nucleation sites. There are some effects which act as stress concentrators. There are some locations where actually when you apply pressure, they become more potent. They actually initiate the phase transition. So you get a nuclei of the martensite and then it goes as you increase pressure. So in case of pressure-induced phase transition, the phase transition should start at pre-existing defects. So it very much depends on the defect concentration of your sample. This is not very important in case of oxide samples or very brittle samples. But in case of metallic systems, this becomes very important. And that is the reason why many researchers report different transition pressures for same system. For example, in zirconium, in static high pressure experiments, there is a range of transition pressure from alpha to omega from 2 GP to 7 GP. So now when you introduce plastic straining to the system, for example, if you don't use any hydrostatic medium and you press the sample between the anvils and you introduce plastic straining, in that case, we permanently generate new defects. So now we are generating new nucleation sites. And at these nucleation sites, the dislocation pileups can be much more higher than what we had in case when we are studying the pressure-induced phase transition. So in principle, the transition pressure actually should reduce. The macroscopic transition pressure should reduce. There is one example recently published where it has been shown that graphite, it actually turns to diamond at pressures as low as 0.7 GPa under pressure and shear. Whereas under hydrostatic conditions or quasi-hydrostatic conditions, people have shown that these transitions takes place at as high as 70. There is an 2 orders of magnitude reduction in the transformation. Of course, this was not the complete transformation. So there were evidence of this transformation at some favorable positions in the time, and it was verified by the TA method. But if we know what kind of stress states leads to this kind of transition, we can actually plan for an industrial scale synthesis process where graphite can be turned to diamond at very low pressures. So this makes the study of plastic strain-induced phase material very important. So one thing is that you can get very low transformation pressures, I mean macroscopic pressures. And then another thing that is a possibility, it can change the reversible phase transitions to irreversible. And because of the straining under the plastic strain, basically the barrier between the initial and daughter phase can drastically reduce. They can be very less transition. So the kinetics of this transition becomes so fast that only strain actually describes the kinetics. So as soon as you increase strain, there will be some transformation. And as soon as you increase strain, you will get the increase in the concentration of the daughter phase. So now your kinetics can be described based on the plastic strain. This is one of the key things to study the plastic strain transitions. Then, using plastic staining, you can also have amorphization, and you can also get the nanostructure measurements. So there is a nice review. Actually, Professor Valery is the pioneer of this area of research, and I would recommend these two publications in order to have more insights about the plastic strain in this case. Of course, I will discuss in detail and mostly discuss things which are described in these review papers in my talks. So with this, end of this talk today. Now we can have some questions. So, can you...
Hello.
Yes, sir.
Yeah, let me ask one question. You have, when we do this Van der Waals kind of a curves and, or for instance, for that matter, Landau theory, where we are explaining this critical point and first order transitions from liquid to gas.
Yes.
Okay, the liquid to gas is a first order transition. But I saw in the literature, even magnetic, ferromagnetic to paramagnetic transition, basically that inverted U with a critical point is, there is an analogy being drawn between magnetic transition and liquid gas transition. I just want to ask whether the in this picture where we are drawing the Landau theory for phase transitions to explain the first order transition, is the transition at the critical point, is it a first order or second order? Because
no, actually, yeah, critical point is an interesting point. So it is the point where your nature of transition changes. So it is no more a first order phase transition; it becomes a second order or continuous phase transition at the critical point.
Yeah, so that is like something like a ferromagnetic to paramagnetic transition at the TC.
Yes. Yes.
Yeah, but does it mean below TC in ferromagnetic transition, where also you will have all those hysteresis in the transitions, while going up and down, you had drawn some hysteresis kind of a lines.
Actually, if you talk about this ferromagnetic transitions in zero field, if you have zero field, then and you consider a single domain, there should not be hysteresis.
Yeah, but you have coexistence of positive domains and negative domains.
Yeah, that is to basically there is a magnetic anisotropy energy. So always in practical systems you have domains.
Mhm.
So that's why you see hysteresis. Otherwise, in zero field there should not be any hysteresis.
Zero field there will not be hysteresis, but at lower fields you will have hysteresis. That
Yes,
can.
yes, definitely. At lower field you have hysteresis. Actually, at lower field, if you see the isotherms in the magnetic field versus your magnetization plots, you can clearly see there will be some instability region. So that you will have some hysteresis at lower fields.
Yeah, but in the Landau theory, you have drawn these hysteretic curves while going up and down in volume or
So I basically try to describe what happens to the Landau free energy in case of external field. So
yeah.
here the external field is basically conjugate variable of your order parameter, which is strain, for example, in case of high pressure static. So in case of this pressure with your stress basically you can consider as a external field. In this case, you definitely see this hysteresis below TC.
Yeah.
So generally, whatever high pressure experiments we do, it is below TC. I mean, we see equally mostly first order phase transitions only under high pressures.
Yeah. So basically, that hysteresis that you had drawn in the Landau theory kind of a curves,
Yes.
that really explains that is the real explanation for the or description rather, not explanation, description for the
First order
hysteresis
phase transition.
across the
Yes.
first order transitions.
Yes, yes.
Okay, but similar thing would be there in magnetic also, ferromagnetic to in the ferromagnetic transition at in the finite fields.
Yeah, definitely. Case of field it should be there.
There is a question on the YouTube. Can every first order transition be converted to second order by applying some external field? This is by Mr. Saurabh Vachal from SSPD.
Yeah, actually, if you see one of the plots that I have shown, can I share my screen again? Sorry. Yeah. If you see this curve, so if you see this curve between the order parameter and temperature, and these are basically lines corresponding to different external fields. So as you increase field, there is a possibility that you can go from first order to second order at some critical external field. But then it should be at some critical temperature, TC. So if you are at critical temperature TC and at critical stress, you can have this second order phase or continuous phase transition.
And yeah, one more thing, the extent of hysteresis you have drawn depends on the that you, whether you are able to make the system so much super cooled or so much superheated. There is a how much you can super cool or superheat depends on the actual physical conditions of your system, right?
Yes.
It is not always you can maximally super cool or maximally superheat. So that hysteresis that you had shown is a maximum that you can get. Normally, you need not get so much hysteresis in reality.
Yeah, so I am basically considering two extreme temperatures, the spinodal temperatures, T1 and T2. So as I am shown in this curve,
Yeah. So that is
sorry, I think, yeah, in this curve,
yeah.
if you don't have any field, so you can see, you can define two temperatures, that's T1 and T2. When your daughter phase just start becoming, you have inflection point here. And is still not stable phase, but it starts basically becoming stable. The phase transition does not happen here.
Yeah, yeah.
Phase transition would happen when your energy of this phase is lower than this. And of course, at temperatures where your thermal fluctuation can allow this crossover of this barrier. At this temperature, when you have T2, when you have inflection point in the first phase, in this case, your first phase actually is not stable at all. You cannot have this phase below this temperature.
Okay. Thank you. So there are no more questions in YouTube also.
I think now we can.
Yeah.
Okay, thank you very much. So next talk will be by Dr. Himanshu Poswal on the high pressure generation. Thank you.